Okay, today we're going to talk about asymptotes and limits around asymptotes. We'll be doing like calculus definitions of asymptotes. You've looked at asymptotes in the past, but maybe not in this way. So here's our definition of an asymptote: line such that the distance between a curve and the line approaches zero as they tend to infinity. We'll deal with and talk with horizontal and vertical. It's a big lesson, so make sure we are attentive. Let's just define these two asymptotes that we have here. We'll start with the horizontal. We'll say this is at B, a y location. And this horizontal asymptote is at a y equals location, so that'd be y equals B. Vertical asymptote, we'll call that at A. And it's a vertical line, so it'll be x equals A. Okay, now, when do these asymptotes occur? Well, vertical asymptotes occur when we look at one-sided limits and they approach an infinity. I'm going to say the limit as x approaches c from the right and the left of a function if that equals either a positive or a negative infinity. Now, we talked about at the beginning of class and last class how limits need to approach a specific value, and infinity is more of a concept. It's not a specific value. However, we are going to start defining at some limits equaling infinity, but know that it's more of a conceptual understanding of what's going on, and it's more of a, hey, what is the behavior of my function doing? So it's more like to help us rather than like a strict definition of a limit, okay? So going back to this vertical asymptote, we would say, hey, if I look as we get closer to A from the left, this function would be approaching negative infinity, right? Because as I get closer and closer to A, but I'm to the left of A, my function is going downward towards negative values. If I'm looking as x approaches A from the right, so I'm going closer and closer to A from the right, my function is approaching more and more positive values. I'd say that's positive infinity. A horizontal asymptote is when we will look at x's approaching either positive or negative infinity. And when those equal values, we'll say we have a horizontal asymptote, including zero. A lot of people forget that zero counts. Now we look back up here. Now, what do I mean by the limit as x approaches infinity? And this is new, having infinity in my limit. It's like as my inputs are growing and growing and growing. So as x approaches positive infinity, I'm looking all the way over here towards positive infinity. What is my function values doing? Well, in this example, my function is increasing. So I would say that this limit as x approaches infinity, that would equal infinity. That means it's not a horizontal asymptote, and there's no horizontal asymptote to the right. But it is something that is helpful to know, to understand the behavior of my function. We're trending upwards as I'm going to the right. If I go to the left, the limit as x approaches negative infinity, I would look at huge negative values over here. We could see that's where we see our function trending towards this y equals b value. And there's that value that we're equaling, okay? In terms of this class, we will be dealing with more horizontal asymptotes in their locations and vertical asymptotes. So we're actually going to start the lesson with horizontal asymptotes. So you're going to skip, and we'll come back to that. And we'll go to horizontal asymptotes. Okay? Now, let's look at this one really quickly. if we wanted to find a horizontal asymptote and we had a calculator available to us, it's actually pretty easy. You know, like we found a limit using a calculator. What is my function approaching? If the function value didn't exist, we would just like plug in values really, really close. In our calculator, we could just plug in big values for x. We can use trace, we can graph. It's a piece of cake, okay? And we'd be able to figure out that the limit as x approaches infinity to this function is 2. And that the limit as x approaches negative infinity is also 2. Okay, let's just do that really quickly. Let me get the calculator out. Just so if you were ever, you know, checking your work on finding a horizontal asymptote and you wanted to use your calculator to check your work, I mean, it doesn't get much easier than graphing. I don't need to put that in parentheses, but I did, just for good practice. Yeah, it's a funky looking function. It's got 2 vertical asymptotes. But we kind of see as you go off to the right, my function values are getting really close to a certain value. And literally just start typing in larger and larger values. Oh, you can't do that. So you would literally start typing in larger and larger values into your home screen, into your function. Does that take more time, or does it still work if you make the window bigger? I bet it still works. Okay, so see we're approaching 2, and I just heard that we can go and just expand our window, and we'll be limited by where our window stops, but maybe that's a little more obvious to see. Y equals 2. Okay, so good. That's the way we can check. But the key is, can we figure this out without using a calculator? There we are. So this guy had 1 at 2, and we kind of figured out that, you know, over here we were approaching 2. Doesn't really matter what the graph looks like. We could get into including the vertical asymptotes, but let's now do it without a calculator. Okay. And we're going to start with this one. And I say there are guidelines. However, I want you to think of more of just like a concept of growth and relative growth of things. Now, the way I'm going to do these problems and find these horizontal asymptotes are different than the way the book does them, okay? You can do it the way that the book does it. It's a little more involved algebraically. This is more conceptually driven, okay? There's a little bit of algebra involved, but it's conceptually driven, okay? And the key concept is the highest power term is going to dominate or be the most influential in determining a horizontal asymptote or a limit at infinity, okay? Let's look at this example. We have this big fraction, 2x cubed plus 1000x squared over 10x squared plus 5x minus 3. What I will tell you is that if you know that this is a limit as x approaches infinity, and only when you see we're plugging in very, very large numbers, can you take this 1000x squared and just cross it off and say, oh, that's insignificant. You might be questioning me right now. You're like, 1000x squared insignificant? What are you talking about? That's a big thing. That's going to affect my numerator. But you're thinking not in terms of large numbers yet. So let's think in terms of large numbers. Let's compare 2x cubed and 1000x squared using different numbers being plugged in. Now, if I start with like 10, so 2 times 10 cubed, that's 2000, right? automatically, that's not even bigger than 1,000 times 10 squared. So it's like, well, that's kind of disproving your point that one's insignificant. Like, why am I crossing out the 1,000 times 10 squared? Okay, like this is smaller than this. Well, let's add some zeros here. Let's go to 1,000,000. So 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so 2 times 1,000,000 cubed is 2 times 10 to the 27th, or 2 octillion. Let's throw 1,000,000 here. 2, 3, 1, 2, 3, 1, 2, 3. All right, notice the difference between this number here, which is 28 digits long, and this number here, which is 22 digits long. They seem to be, relatively the same. But watch what happens when I divide the two. There you go, sorry. And then I divide this by that. Okay, the top number is 2,000,000 times the size of the other one. Now, if you think about that conceptually, and you're adding the second number, the bottom number, to the top number, it's almost like taking 1 and adding 1 over 2,000,000. What do you get? A number that's essentially still 1.000000005, right? So if I'm adding this smaller number to the bigger number, it's not doing much to it at all, right? So now that's the kind of concept that we're thinking about with cross this off, it's insignificant. But I didn't go far enough. I only plugged in 1,000,000. That's still thinking small in terms of big numbers. Let's talk about 10 to the 100th. We get 2 times 10 to the 100th cubed is that digit. It's that number, 301 digits long. And let's see what it is if I plug that same number in for x and square it. It's 204 digits long. Now, still a big number, but relatively to this number, it is much smaller. Watch how much smaller it is. How many times the size the cubed number is than the squared number. It is 2 untrigatillionths times the size. It is essentially like taking 1 and adding 1 over that. That's not exact, guys. Okay? So notice this is the decimal approximation. Hold on, all right, there it is. All right. So adding those two numbers together is like adding these two numbers together and getting this. Is it changing what you have? No. You're essentially still at 1. So relative growth means if you're not growing as fast, you are insignificant when dealing with big numbers. Okay? That's why 1,000x squared just got crossed off. That's why 5x can get crossed off in the denominator and 3 can get crossed off in the denominator. Because they'll be insignificant when being added or subtracted from 10 times our number that is huge being squared. Okay? Well, now, the problem gets easier. Let's just say, well, this is the same as the limit as x approaches infinity of 2x cubed over 10x squared. Now, I couldn't have done this before because I had all these pluses. And when we have addition, simplification is not so simple. But when I have multiplication, simplification is simple. Some x's will cancel. I can even cancel the 2 and the 10 if I wanted to. And I could say, well, this is just essentially the limit as x approaches infinity of x over 5. Well, if I plug in a huge number in for x and I divide it by 5, what do I get? What do I get? Huge number divided by 5. Yeah, well, it's still going to be a huge number. And we're going to still say it's so huge that it's infinite. Infinity divided by 5 and still infinity. Infinity divided by any number is still infinity. Infinity divided by infinity, don't do. You don't know what that is. That could be anything. Okay, but divided by a number, it's infinity. So in a situation like this, we have a situation where we don't have a horizontal asymptote. However, we know that as, if we're looking at a graph, as we're going out to the right, my function would be trending upwards, which is important to know. And I figured out relative growth rates made things easy. Now let's look at this next one. Again, 4x cubed minus 20x. I'm plugging in huge negative values now. Huge negative values. Well, huge negative values plugged into negative 20 times x are still going to grow significantly slower than huge values being cubed and multiplied by 4. So I'm going to go ahead and just cross this off. I'm going to go ahead and cross this off. I'm going to make this problem a lot easier. I'm going to say, let's just find the limit as x approaches negative infinity of 4x cubed over 1000x squared. And you could go even further and say this is the same as the limit as x approaches negative infinity. I'm not even going to bother to simplify the fraction. What's 250? Sure, I can simplify it. X over 250. But now we have to be careful when dealing with infinity. Infinity can be infinitely large and positive or infinitely large and negative. Here, this is infinitely large and negative. So I have a huge negative number divided by 250. Still going to be a huge negative number. This is important to understand that it could be negative because as I'm traveling to the left, my function would be trending downwards to bigger and bigger negative values. Okay? So that's the first situation if my numerator kind of is growing faster than my denominator. Second situation, if my denominator is growing faster than my numerator. Now, here's a concept, and sometimes we have trouble thinking about infinity. Well, infinity divided by a number, we say is infinity. What if I have a number divided by infinity? What's that? Discuss that with your neighbors. What if I have like 5 divided by 1 followed by one of those numbers that I showed you earlier? What's that going to pop up in my calculator as? Discuss. Go ahead. Discuss. All right, Mr. Sun, I'll go with you. What do you think? Right. It's like 0.0 repeated, so many zeros followed by a number that it's basically essentially 0. This is a huge concept in this class. Something that is like infinitely small, we can say is essentially 0. Like adding point whatever to 1, it's still 1. It's just got a little bit left after it. We will say it's essentially 0. Okay, so that's important to know, and I'm saying k is just a constant. Well, let's look at this one. We can work our way to this situation by first crossing off the 20, finding the limits as x approaches infinity of negative 5x to the 4th over 2x to the 5th. The x's will cancel, giving me the limit as x approaches infinity of negative 5 over 2x. Now, if I think about it conceptually, I plug in a huge number, multiplied by 2 would be a huge number, and I'm dividing it by negative 5, or dividing it into negative 5. Well, it's going to be essentially 0. I don't care that I have a negative in the top and a positive huge number in the bottom. I'm just still going to say it's going to be 0. I can say it's approaching 0 from the left side, but whatever. Let's just keep it there. Okay? All right. So this guy, same deal. Now notice I have a negative symbol. It won't change things in the way you treat this. Relative growth, we don't care about the x squared and the 2x. I have the limit as x approaches negative infinity of 5x to the 5th over x to the 6th. This is 5 over x. As x approaches negative infinity, the 5 over a very large negative number still would be approaching 0. Okay, so for all of these, whereas the previous ones we didn't have horizontal asymptotes because we were approaching infinities, these have horizontal asymptotes. They're at 0. Okay. Well, we can look at the relative growth rates when they're the same. So again, same type of situation. I'm trying to find the horizontal asymptote by looking at the limit as x approaches infinity. The 2x, negative 5, this 1, insignificant when plugging in large, infinitely large values. So I'm really just finding the limit as x approaches infinity of negative 4x cubed over x cubed. Now watch what happens. The growth rate in my numerator, that x cubed, is growing at the same rate as my numbers are growing in the denominator. Those growing numbers will essentially cancel each other out, leaving us with just the limit as x approaches infinity of negative 4. Well, if this is just y equals negative 4, we would say this is just negative 4. So now we found a horizontal asymptote at a different value other than 0. Because the growths cancel each other out. Let's look at the signs. What if we are approaching negative infinity with a similar problem? Well, again, now all of these are very simple because they're in order of growth. Be careful on problems on homeworks and on quizzes to find the ones with the biggest degree. Also, never cross things off if this isn't an infinity. Like, make sure you note, because this is infinity, I'm doing this kind of growth rate comparison process. If I'm talking about the limit as x approaches 1, well, when I plug in 1 everywhere, adding 5 is going to make a big deal, okay? Subtracting 2 will make a big deal. Don't cross it off because I'm just plugging in a value. I'm plugging in infinitely large values, which is why I can do this, okay? So please take note of that, and then understand that we actually don't have to be careful with signs because they're just going to cancel each other out in both the positive direction or the negative direction. We'll just get negative 2. Okay, you guys do the next 3 and compare your answers with a neighbor. Okay. Check your answers. Not working. Okay, so Mr. John, what did you get for the first one? Mr. Minion, nice. No horizontal asymptote. I guess I called you John, yeah. Miss DeJean, we would say this is approaching positive infinity and negative infinity, depending on where you're looking. Miss DeJean, what about for the second one?
Like 2/3.
Good. The horizontal asymptote would be at 2/3. And then the third one, Miss Drew.
Yes, 0.
0. All right, good. We can do these three if we haven't done so already. I'm going to do them quickly. You can just check your answers once you've done them. So this is where people sometimes have some difficulty. For this one, you could cross out the 4 and you would be correct to do so, and it's fine. That's because this is like x minus 4, and as x approaches infinity, it's an infinity minus 4. Still infinity. But this one is different. I can't cross off this 5 because as I'm plugging in bigger and bigger values for x, we'd have 2 over infinity, which is essentially 0. We'd end up with 5 minus 0, which is 5. So be careful. Do not just cross off everything that you think you can. It's only in certain fractions where x is involved. Questions? Yes. Yep. Well, x minus 4 as we're approaching infinity would end up being infinity minus 4, still infinity. Right? Ever increasing number minus 4. Right, so there'd be no horizontal asymptote. Dot 0, there wouldn't be a horizontal asymptote. We'd be approaching the infinities. Does that make sense?
So that's the same as saying no horizontal asymptote?
Yes. I would like you to keep track of the direction, though, that we are traveling in. As we're approaching positive infinity, this would be approaching positive infinity. And as we're approaching negative infinity, I'd like you to answer this as being negative infinity. But this is the same as saying there is no horizontal asymptote because our function is not approaching a horizontal line. It's going up diagonally, downwards diagonally. Does that make sense? Okay. Do the next 3. Okay, you can check your answers with me. I did not go the full simplification, did not do the full simplification of all of these. I kind of left it after we canceled out the things that are insignificant. Any questions about any of these? Okay, the next ones are a little bit trickier, involving infinity. I'll show you why. Keeping the same growth rate concepts and understanding we're plugging in infinity, that 2 doesn't matter, that 1 doesn't matter. You start simplifying this algebraically. Watch what happens. Now, with the plus 1, I can't simplify this root 2x squared. I would just keep it as root 2x squared plus 1. But once I get rid of the plus 1, I can change this to be 3x over root 2 times root x squared. Okay, I can split it into 2 separate radicals. It is just an exponent. Okay, now what happens now is that this root of x squared, you can simplify to just be an x. However, the original x could have been positive or negative. We say that could be a plus or minus x. Well, the x's will cancel, and it'll leave you with a 3 over a root 2. But we still have this plus or minus. That makes things interesting. Now, I don't like to go all the way down to here. I like to kind of stop here and understand that my answer is going to be either positive or negative 3 over root 2. It's one or the other. For both this first one and the second one, which is the same thing. But it's not both of them. It's one or the other. So we got to pick the right one. Now, I kind of think about the signs of things and think about just my properties of, multiplication and division when dealing with signs. If I'm plugging in a positive large value and I multiply it by 3, I know my numerator is going to be a positive. If I plug in a positive large value, square it, multiply it by 2, that'd be a positive, square root it. Well, it's only when you're taking the square root of a unknown squared that you could say the original unknown is positive or negative. If I'm just taking the square root of a positive, I just get a positive. It's not a plus or minus. And this is a positive. This is why I know that we have a horizontal asymptote at positive 3 over root 2 as x is approaching positive infinity. But for the second one, same thing holds, but I'm approaching negative infinity. Well, again, thinking about signs, it'd be 3 times negative infinity. That would make this numerator a negative. The denominator would remain a positive. It is a negative value squared, which is a positive, times 2, which is a positive, square rooted remains positive. This is why I know that to the left, we have negative 3 over root 2, which means this function with this square root has 2 horizontal asymptotes. We're used to just having 1. Okay? Now we need to be careful. We just can't assume that when we're going in the negative direction, we're going to have the negative, 3 and root 2. Okay? We have to be careful with our signs. Go ahead and do this third one. Check your answer with a neighbor. Well, the square root of x squared we said was x, so it canceled. with this x.
Oh, okay. Oh,
So-
this is the same one. Okay.
Same one as that. Yep. Now, very important. Square root of 4 is just 2. Okay? Square root of 4 is not plus or minus 2. Square root of 4 is 2. You can only take square roots of positive numbers and you get positive numbers. Only when we have the square root of x squared that we have this plus or minus. I would do the following. Understand that the 5 doesn't matter. Have the limit as x approaches negative infinity of negative 6x over root 4x squared. This can simplify as root 4 root x squared. Root 4 is just 2. Root x squared is plus or minus x because it is an unknown. The original unknown could have been positive or negative, which is allowing us to square it and then square root it. Okay? These x's will cancel. I end up with 6 over 2, negative 6 over 2, but could be positive 6 over 2 or negative 6 over 2. We have to figure that out. So I know it's going to be 3 or negative 3. I go back up to this one, and I kind of like to stop here, understanding it's 6 over 2. I plug in a negative value. I have negative 6 times negative infinity. This is a positive. The denominator, negative infinity squared, positive times 4, positive square rooted positive. So this is why this is a positive 3. Okay, a little tricky, just need some practice. Okay?
When we do our homework, you want to file.
No, just get the right answer. However you get the right answer, get the right answer. All right, let's talk about trig functions like sine of x. The limit as x approaches infinity. We should know that sine will not approach a value. It just will oscillate. It'll go up and down and up and down and up and down forever and ever and ever. So we say this limit does not exist. It will be at most 1 and at least negative 1. It goes off to the left this way too. So negative infinity does not exist. Okay? So sine doesn't grow, just oscillates. No growth to it at all. All right. Discuss this with your neighbor. What do you think that is? Sine and cosine do not grow. Ms. Kaiser, what do you think?
Not really sure
Yeah?
what
Okay. But you were saying something, which is why I called on you. What were you saying?
If sine doesn't ever go past negative 101, but x could go past those numbers,
Mm-hmm.
and it would be like having like some side number over a potentially infinitely larger, smaller.
And what is that? When you have just like a number divided by something that's infinitely large.
Yeah.
And that's correct. Sine's not growing, x is growing. So, no growth divided by growth, 0. Here, Think of sine as a constant. It's not going to affect what 2 times a huge negative number is going to do. I can actually cross sine off. It doesn't grow. This is just x over 2x. As we're approaching negative infinity, that's just a half. Okay? Well, try that one out for size. What do you think, Mr. Pittman? Yes. How'd you get 1 out of all this?
I wasn't completely sure.
Mr. Plummer helped?
Yes.
Mr. Plummer, how did you get y equals 1?
Then on the divided by infinity would be 0, then we times 2.
Yep. 1 over infinity is essentially 0, so this is going to trend to 0. So it's essentially, what is the cosine of 0? That's 1. That's interesting. Now, what about this one? Okay, this is very interesting. As x is approaching 0, from the right, we have 1 over something that's very, very small. That's positive. What is something divided by something very, very small? Something really, really big. Good. Okay, so it's important to know that 1 over something really small, we'll talk more about this in a second. 1 over something very, very small is something very, very big. What is the sign of infinity? Do we say that's infinity? No, we talked about it earlier. This does not exist. Okay, does not exist because sine oscillates as I plug in bigger and bigger values. It goes up and down. Because it's cosine of 0. This is the sign of infinity. Notice this is different from that. I just kind of threw something different at you. Not kind of asking you about a horizontal asymptote there. Okay. Now we have to look at other types of functions and their growth rates. What grows faster, x cubed or 3 to the x? 3 to the x. So much so that I can compare 3 to the x to any power, x to the 1,000, and 3 to the x. 3 to the x wins. Okay? A number to a power grows much, much faster. Exponentially fast is what they call it, an exponential function, compared to a polynomial, x to any power. Okay? 3 to the x wins. 4 to the x is better than 3 to the x. Log x is the slowest growing function. It is the inverse of e to the x, which is an exponentially fast growing function. Just e is a number that we'll talk about more later, 2.717. You can just know its decimal approximation. Log x, its inverse. It is the slowest growing function. Okay? That's what it looks like. Slowest growing function, fastest growing function. As x is approaching infinity, here's how you're going to list the growth of functions. You have first constants, C for constants, or trig functions like sine and cosine. Those are all the same. They don't grow. Then we will have stuff that grows but grows exponentially slowly, log functions. This is slow to fast. Then stuff that grows x to powers, it will grow fast, but it will not grow anywhere as fast as numbers to powers, numbers to x powers, which will grow the fastest. Including in here is like 2 to the x, 3 to the x, e to the x, all those. Okay, no growth, extremely small growth, growth, exponential growth. So knowing that, we no longer have maybe algebraic means to help things. We have more of the conceptual idea of growth and what grows faster than what. So I can ask you which one equals 0. We have 3 situations. Okay? What I would approach, I'd say x to the 99, that's going to grow faster than log x, which is the slowest growing function. So I'm talking about something that's growing faster than in the numerator than in the denominator, which means these numbers in the numerator will be bigger numbers than the numbers in the denominator, which means this will trend towards what number? Infinity. So that doesn't equal 0. The third one, e to the x, is going to grow faster than x to the 99, which is growing slower. Because e to the x is growing faster, there's no algebraic way to kind of simplify this. You just know that it's faster and this is slower. Bigger numbers, smaller numbers. Bigger is divided by smaller will be ever increasing bigger numbers. The middle one, log x, slowest growing function, over an exponentially fast growing function, that will equal 0. Okay? This next one, when we have exponent powers, we can cross off now x to the 99th, the 2, the 1000x squared. We can look at e to the x and compare it to 3 to the x. You got to remember e is around 2.7, so 3 to the x is going to grow faster than e to the x. So this would be approaching infinity. We wouldn't have a horizontal asymptote. That would be its behavior. However, it gets complicated with these exponentially fast-growing functions. Because this is true, it's going to trend towards infinity and then very quickly. But this is false. That's wrong. What is 3 to the negative infinity?
1 over 3.
Exactly. We can use an exponent rule to say that it's 1 over 3 to the positive infinity. What's 1 over an infinitely large number, essentially? 0. That changes everything. Watch, if I ask you what's the limit as x approaches negative infinity of this same problem that we just did. Okay, probably copy it down one more time. Notice that I have a negative infinity. We can't cross off the x to the 99th. We can't cross off the 1000x squared. Why? Because as we're approaching negative infinity, this fastest growing exponential function turns into essentially a constant. It turns into a non-growth function. And this turns into a constant. So it's actually in this direction, that goes away, that goes away. And this goes away. As we're approaching negative infinity, this is growing faster than this. It ends up x to the 97th over negative 1000. This is interesting. Plugging in negative infinity to the 97th power would remain negative. Divided by a negative would be a positive. Okay, so sign doesn't matter. So let's just skip that second one, go to this last one. If I ask you to find the horizontal asymptotes to this guy, g of x, what we need to understand is that we're going to have two answers, and we need to approach this in two ways. One as x approaches positive infinity, and one as x approaches negative infinity. Go ahead and find both of these answers. First one would be approaching positive infinity. E to the x will dominate the growth. It'll go faster than x to the fourth. Positive infinity wins. But as x approaches negative infinity, the e to the x would go to 0. The 32 would not matter. We'd end up with 2x to the fourth over 4x to the fourth. This would be approaching a half. Okay? Great, that was all horizontal asymptotes. We spent most of our time on the things that you will be tested on and quizzed on the most, but there are some horizontal asymptotes we got to talk about. I mean, some vertical asymptotes we have to talk about. Okay, and really we want to figure out just the behavior of functions around an asymptote. Now I'll tell you, typically for a function like -2 over x over 3, if you ever have a number over 0, that's an indication that you have a horizontal asymptote, vertical asymptote at that location. I can just go ahead and tell that right now, this function will have a vertical asymptote when x is 3. Okay, but the question is, how is my function trending around 3? Is it going up to the left, down to the left? Is it going up to the right, down to the right? You know, what is the behavior around it? With a calculator, obviously, it's easy. Here's what I do without a calculator. I look at the one-sided limits, and I try to figure out by using values like I would in my calculator what this would look like. 2.999 minus 3, that's going to be a number that's really, really close to what? 0. Is it going to be positive or negative? It's going to be negative. 2.999 is a little bit less than 3, right? I'm going to say that's going to be 0 from the left. Here, if I use 3 to the right, that's going to be like 3.0001. If I subtract 3, it's going to be -2 divided by something that is close to 0. But since it's a little bit bigger than 3 minus 3, I'm going to say that's positive. Now, again, if I have something divided by something infinitely small, what's this going to be? Infinitely large, right? As long as we understand signs, and like positive divided by a negative is a negative, negative divided by a negative is a positive, I could tell that this, as we're approaching 3 to the left, will be approaching positive infinity. As we're approaching 3 from the right, this will be approaching negative infinity. Why? Negative divided by a negative, positive. Number divided by something infinitely small, infinity. Here, negative divided by a positive, negative. Number divided by something infinitely small, something infinitely big. That's how I can tell that close to 3, my function's trending like that, from the right and from the left. Okay, so this is a negative divided by a negative. This is a negative divided by a positive. Okay, let's do, and the notation that I'm using is like 0 from the left is something infinitely small and negative, and 0 from the right is something infinitely large or infinitely small and positive. We'll skip this one. This one's easy. What are these two? Look at this, x approaches 4 from the left. Well, I plug in something like 3.999. And I just think about the concepts. Not doing it with my calculator, I'm just kind of doing it with my knowledge of math. Now, this is like 4 minus 5, which is negative 1. And it's negative 1 from the left, but I actually don't care because it's still negative. This is going to be something that's very small and negative. This is why I know this is positive and large. That's the idea. I have more examples on my video, which you can watch online if you want to finish these notes. But we got through the more important stuff, which are the horizontal asymptotes. If you have any questions about the vertical asymptotes on your homework, anything like that, please ask.